morning and welcome back to For the Love of dPCR 2024, an immersive virtual event dedicated to exploring the remarkable capabilities of digital PCR. We're thrilled to have all of you join us today. As a reminder, by registering for this year-long event, you will have exclusive access to ongoing content updates and insights from dPCR experts, empowering you to propel your own work forward. After today's session, we encourage you to explore our virtual environment where you have access to our poster hall, booth, and virtual labs, which have ready-to-download content, videos, and even podcasts to help you get started no matter where you are in your digital PCR journey. Today, we are thrilled to introduce the launch of our most recent digital PCR system, the QuantStudio Absolute Q AutoRun Digital PCR Suite. We are joined today by Donnenwirth and Dr. Chandler, who will be introducing us to the AutoRun system and showcasing how this scalable digital PCR solution can help to support both efficiency and productivity. After that, please join us as Dr. Bauer will walk us through the foundations of digital PCR and will help demonstrate how the power of consistency can help improve accuracy across a number of digital PCR applications. Now let's kick off today's event. It's my pleasure to introduce our first speaker, Donnenwirth. Dana holds his Bachelor's of Science in Bioengineering from the University of California, Berkeley, as well as earning an MBA from their Haas School of Business. He's a senior product manager for qPCR and dPCR instruments and has been with Thermo Fisher Scientific in both technical and business roles since 2009. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply enter them into the Ask a Question box and click Send. We'll answer as many questions as we have time for today at the end of the presentation. Dana, you may begin your presentation now.
All right. Thank you, Christina, for the introduction. I am excited to be here today to share about our new launch of the QuantStudio Absolute Q AutoRun Digital PCR Suite. Let's start with what makes digital PCR unique. Digital PCR quantifies your target of interest without the need for a standard curve, and it achieves this by dividing a bulk reaction into thousands of smaller, independent reactions to leverage the power of Poisson statistics. But one important note here is that digital PCR and real-time quantitative PCR are complementary technologies, and each have applications that they serve best. Now, the key to effective digital PCR is robust, consistent compartmentalization of the initial bulk PCR reaction. While some methods use fluidic shearing to create droplets, others use nanoplates with fixed microreactions. The method selected can have a major impact on the number, size, and consistency of microreactions, all of which can have a major impact on overall data quality. Additionally, many methods require a larger overall sample volume to account for the overage needed for the actual reaction creation process. So with a quick introduction to the technology itself, the question then is, what is digital PCR a good fit for? The answer is applications that include any time you need robust absolute quantification, with the primary example being the quantification of viral titer. Another is when there's a need for accurate measurements of low abundance targets, such as when identifying residual host DNA in a biologics manufacturing process. Additionally, because of the microreaction volume, digital PCR can be a good option for samples that are challenged by the presence of inhibitors. Before we go further, I would like to call out that there are numerous limitations associated with other digital PCR technologies, not all of which are droplet-based. As I previously mentioned, the foundation of digital PCR is the subdivision or the digitization of a bulk PCR reaction into independent microreactions. So again, the method by which this is accomplished can have a huge impact on the quality of data and the associated workflow. So other digital PCR platforms suffer from 5 major limitations. The first is significant wasted sample, sometimes referred to as dead volume. Wasting precious or expensive samples and reagents is always to be avoided. But what is arguably more important is the fact that this dead volume can lead to significant subsampling error. Digital PCR is often used when looking for a needle in a haystack, so you want to analyze as much of that haystack as you can. If you throw a bunch of the haystack out, there's a good chance you may miss that needle. Number 2 is limited or inconsistent compartmentalization. 20,000 microreactions is generally considered to be the sweet spot for most digital PCR applications, and it is imperative that this number be consistent from sample to sample. Droplet-based approaches to digital PCR suffer from high variability in the number of droplets generated per sample. Similar to high dead volume, this can also contribute to subsampling error. Number 3 is a tedious workflow. Many digital PCR platforms require multiple instruments and extensive human intervention. Not only is this inconvenient, it can lead to inconsistent results. Additionally, more instruments and moving parts means greater potential for service issues and frustrating downtime, not to mention more space and more training required. Number 4 is long turnaround times. Some digital PCR platforms can take as long as 6 hours to generate a single data point. And number 5 is that it's endpoint analysis only. Most other digital PCR platforms analyze endpoint data only, telling a user if those microreactions are positive, negative, or perhaps somewhere in between after PCR has been completed. This limited insight can lead to greater potential for false positives. Addressing these limitations is where the Absolute Q digital PCR system really shines. Its design ensures efficiency in reagent and sample use with less than 5% dead volume lost to the process. It also hits that sweet spot of digital PCR with 20,000 microreaction partitions per sample. And setting up a plate is extremely user-friendly because it follows a workflow equivalent to qPCR, with a bulk reaction being pipetted into the plate, plus a simple capping procedure. Finally, results can be achieved in 90 minutes, and powerful analysis software with false positive rejection capabilities provides elevated confidence in results. To dive a little deeper, many advantages of the QuantStudio Absolute Q system are driven by its MAP16 digital PCR plate. The MAP16 plate is built for optimal compartmentalization of sample with a major focus on 3 key factors. Number 1 is consistency, or the ability to reproducibly create thousands of small reaction volumes. The second is precision, or the ability to define each reaction volume with high confidence across various sample types. And the third is accuracy, or the ability to use as much of the loaded reaction volume as possible to quantify those targets. And each MAP16 plate can run up to 16 samples in parallel. However, partial plates can be run in intervals of just 4 samples, and unused arrays can be preserved for later use. Each one of those 16 arrays consists of exactly 20,480 fixed microchamber partitions, and to fill them, 9 microliters of bulk PCR mix is loaded into each array, and over 95% of that input volume is digitized and analyzed, with a very small dead volume of less than 5%. And additionally, each array sees a very high microchamber fill success rate of greater than 99%, enabling unparalleled digital PCR consistency. And just as a follow-on, a comparison study of the map-based QuantStudio Absolute Q and a droplet-based platform shows the superior digitization consistency and the lower percentage of wasted sample with the Absolute Q digital PCR system. And building on this is the following example of an ITR2 viral vector quantification application, where the QuantStudio Absolute Q, with its microfluidic array plate technology, those data points shown in blue, supports greater precision and consistency across multiple plates as compared to the results from other digital PCR technology platforms, whose data are shown in red and in green. So to summarize here, the QuantStudio Absolute Q MAP16 plates and the associated digital PCR software can easily scale to accommodate your desired throughput. Their versatility lets you break free from the limitations of a 96-well plate footprint, so you no longer must wait for a perfect 96 sample batch size, waste partial plates, or split batch sizes larger than 96 samples. With the ability to run arrays in multiples of 4, along with the ability to batch up to 24 plates, which is 384 samples, all into a single analysis study, the Absolute Q system can let you perform your experiment as desired. But what if you need greater throughput or more operational efficiency? Or what if you need more flexibility to support multiple users, all needing the equipment simultaneously for their individual studies? This is where the Absolute Q AutoRun Digital PCR Suite comes in. The AutoRun Digital PCR Suite is a combination of systems, including the Absolute Q and the Spinnaker microplate mover robot. It is a scalable, automated platform that enables labs to significantly improve their productivity. All Absolute Q systems have the capability to be upgraded to AutoRun systems, presenting a solution for scalability now or in the future. With our advanced automation technology, you can save time and effort by simply loading your plate at any point during the batch. The AutoRun system takes care of plate scheduling and loading, allowing for seamless operation. Furthermore, different users have the flexibility to run their own protocols and assign priority to their respective plates. By utilizing an AutoRun system in unattended mode, you can conveniently schedule and process up to 12 plates, 192 samples, for overnight processing. And the data generated from these runs can be easily combined and analyzed together using the software's study mode, facilitating a streamlined analysis process. To summarize, the AutoRun Digital PCR Suite takes all the advantages of the Absolute Q system and its MAP technology and amplifies it with automated plate handling and run scheduling. The result is greater utilization and multi-user flexibility to truly elevate a lab's efficiency in leveraging digital PCR technology. And if even greater throughput and walkaway automation are needed for maximizing sample processing and data output, the AutoRun Digital PCR Suite with a dual Absolute Q configuration will be coming soon. This system will be capable of processing over 1,000 samples in 48 hours, completely unattended. And a key component to the AutoRun Digital PCR Suite is the new QuantStudio Absolute Q digital PCR software. It's been designed to improve workflow efficiency and reduce the risk of human error in digital PCR workflows. It offers faster analysis, streamlined template-based run setup features, and preset thresholding and dilution factors. Additionally, the software includes enhanced analysis features that provides users with better insight into their digital PCR data, including confidence intervals and precision alongside CNV calculations. The software also includes integrated dilution factor correction to ensure accurate data interpretation, along with improved quality control tools that provide valuable insights into QC flags, all simplifying the results reporting process. With all these advancements, the new software empowers users to achieve more accurate and more efficient results with their digital PCR experiments. And I want to highlight one of these key software enhancements, which is its ability to provide robust false positive rejection and QC. To this end, the Absolute Q analysis software applies advanced criteria to qualify individual microchambers. This process includes first checking that the fluorescence level of the reference dye, which is ROX, falls within the acceptable expected range for each microchamber. Second, subtracting pre-PCR scan values from post-PCR scan values to eliminate any anomalies, such as autofluorescent dust, debris, or other imperfections. And third, employing artificial intelligence to ensure that each accepted microreaction exhibits what is considered normal behavior. All of this enables greater accuracy and confidence in the digital PCR data and the reported results. And just as a quick note, all the power and productivity of the Absolute Q AutoRun digital PCR suite is supported by our superior service plans, with multiple options available depending on the extent of your needs for qualification services, application support, and the availability of technical support personnel. Additionally, covered instruments also benefit from prioritized service if necessary. And just briefly on applications. Paired with the QuantStudio Absolute Q digital PCR system is a growing assay menu of Applied Biosystems TaqMan assays. These assays provide the gold standard performance you've come to expect from the TaqMan portfolio, all specifically designed for optimal performance on the digital PCR system. Thus far, the application focus areas for these assay families are around oncology and therapeutics discovery. The cancer research assays are designed for rare target detection of common cancer mutations in liquid biopsy samples, and the therapeutics research assays are designed for biotech and biopharma customers for viral titer quantification. All pre-designed assays at launch are wet lab validated for use on the Absolute Q digital PCR system. And if you're interested in other areas, there is always the option for custom digital PCR assay designs as well. In conclusion, digital PCR is all about getting consistent, accurate, and precise data. And it would be nice to accomplish this quickly with little human intervention. Competitive platforms make you choose between high-quality data and simple workflows. But when it comes to the QuantStudio Absolute Q, the simple workflow itself enables superior quality data without sacrificing time or expensive reagents. And now, with the AutoRun suite, you can take your digital PCR workflow to the next level of productivity and flexibility with the power of automation. Thank you very much. And now I will take any questions.
Thanks, Dana, for that really great presentation. We have time for just a couple of questions, so I'll read those that have come in through the chat, and if we don't have time to get to the rest of them, we'll be sure to follow up by email. But the first one that I see is, can I analyze multiple plates on the AutoRun together?
Yes, you can use the study mode with the AutoRun and the Absolute Q software, and you can analyze up to 24 MAP16 plates together.
Great, and it looks like the second question we have is the DNA stable at room temperature overnight?
Yes, we have done some studies with the assembled reactions, and the DNA is stable overnight, and we continue to kind of extend out that stability for longer periods of time with the AutoRun use as well.
Fantastic. The third question that I see coming in is, I'm very used to real-time PCR. Is the workflow of dPCR very different?
Definitely not very different. They are extremely similar in just setting up a bulk PCR reaction mix, master mix, sample, primers, and pipetting into the plate. And pretty much from there, you're good to go. So if you know qPCR, you know dPCR.
Fantastic. And our last question I have in here is, if I decide that a single configuration Absolute Q supports my current needs, but I decide later that I need more throughput, do I need a completely new system to get the dual?
No, so we've designed the AutoRun system with scalability in mind. So you can start with just a Absolute Q and upgrade to our single configuration AutoRun. And then from there, if you need even more throughput later, You can add an additional Absolute Q unit to make a dual configuration auto run. So from the very low throughput all the way up to the high throughput, we have you covered.
Fantastic. Thank you so much. So thank you again for all of our participants for submitting questions. If we didn't get to your question, or if you have questions for Dana throughout the rest of the event, please feel free to continue to submit those questions, and we will be happy to follow up with those questions via email after the event. Thank you again, Dana.
Thank you.
Now we're going to move on to our second topic with Dr. Chandler Walker. Dr. Walker will be covering the keys to efficiency and getting the most out of your digital PCR system. Dr. Walker received her PhD in cellular and molecular biology, investigating localized RNA translation in neuronal axons. She then completed a postdoc in the pharmaceutical industry, working on target validation for neurological disorders. In 2019, she joined Thermo Fisher Scientific as a field application scientist supporting real-time PCR, digital PCR, and sample preparation technologies before transitioning to a service product development role, supporting automated real-time PCR and digital PCR platforms. She is now a product manager supporting the QuantStudio Absolute Q AutoRun digital PCR suite. Just as before, we encourage you to participate by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. Dr. Walker, you may begin your presentation.
Thank you so much, Christina. Today, we will be talking about how you can optimize efficiency using the QuantStudio Absolute Q AutoRun digital PCR suite. To start, let's just talk about why efficiency is important in your digital PCR workflows. There are several key benefits to having a more efficient digital PCR workflow. The first is consistency. Our AutoRun system offers workflows that are very simple, easy to use, easy to learn, easy to onboard. So if you have new people joining your lab, it's a quick transition period to get them onboarded. You also can have improved utilization. The AutoRun system has overnight unattended operation capabilities, so this means that you can maximize the use of your Absolute Q instrument. Lastly, it's convenient. The AutoRun allows for simplified coordination and prioritization across systems that might have multiple users. A quick overview of what we'll be talking about today. We'll start by talking about the types of files that you will interact with within the Absolute Q AutoRun system. One of those types of files is a template file, so we'll spend some time talking about templates and why they can be used to improve efficiency. Next, we'll move on to the types of workflows that are available using the Absolute Q AutoRun system. And we will talk about batch creation of run files, and this is associated with one of those types of workflows that I'll talk about previously. Lastly, we will go through an overview of what an AutoRun system workflow looks like. There are 4 different types of files that you have access to within the QuantStudio Absolute Q software. To start, you have a template file, also termed a .dpt file. And this can be made from scratch, or you can also create it using a completed run or a draft run that we'll talk about in a second. And this type of file can be used to predefine various protocols and analysis settings that we'll talk about on the next couple slides. A template is used to generate draft run files, or DPR files. This is a file that has not been run yet, so this is still fully modifiable. You start a run using this DPR or draft run file. Once that run is completed, that draft run is then converted to a completed run. And this file type is a .zst file. What is great about our software is that you can combine your completed run files, those ZST files, all together into a larger study, and you can analyze your files across all of those files together. So this is a great opportunity to streamline your analysis workflow, and we'll talk more about studies at the end of this talk. Within the software, if you are creating a template, you have quite a lot of options that you can predefine. These include your cycling parameters for your digital PCR run, including the temperatures, the amount of time that you spend at each temperature, the number of cycles that you are repeating for that PCR. You're also selecting your various dye channels. So this depends on which dyes you are putting into the wells of your plate. Another way to improve efficiency here is that once you have defined that specific protocol that you will be using, you can actually export that protocol and save it and continue to import it into future templates so that you can save time not having to continue to predefine all of your protocols from scratch. In addition to the cycling parameters, you can also predefine your analysis settings across your various groups. You can predefine the groups within your plate. You can define whether they are simply individual samples, whether they are replicates of the same sample, or they might also be pooled samples, and you can designate these all within your template. For each of your various targets, you will assign it to the corresponding dye channel. And you can also predefine the type of analysis that you are performing. If you are performing copper number variation, for example, you can designate this here. And you can also distinguish between a sample that you are measuring the copy number variation, or if this is a reference. Lastly, you can designate the way you would like to threshold these particular targets. You have the option to use the auto thresholding capabilities of the software, and you can automatically threshold across a defined group, or you can automatically threshold specifically that sample. If you do have a predefined threshold that you have manually set, you can designate that within the template as well. I wanted to bring up these types of file types because they are at the heart of the different workflows that are available for the AutoRun system. The first type of workflow is leveraging that template or DPT workflow. This is best used if you have a large study where you are applying that exact same protocol and also analysis settings, if you have them predefined, to every plate that you are running. And this is regardless of the plate barcode. Every plate that you put into your system will have exactly the same protocol. In this scenario, you can import your sample IDs into your run files after the runs have been completed. An alternative, more flexible solution is our dPR use case. So this is a workflow where you are now utilizing those draft runs or dPR runs. This enables you to run a variety of protocols and analysis settings across different plates. So if you have different users that are using the system, this is a great opportunity for them to each define their specific protocol. The way that the system works is that we'll apply the appropriate dPR file to a plate based on a specific barcode. So when you are building out your dPR files, you're assigning a barcode to that file. This does enable users to specify their sample IDs that are associated with that plate barcode prior to running the experiment. One thing that you will note about the dPR workflow is that it does require you to create a dPR file for every plate that you are running in your system. So we built in capabilities within our software to make this process of DPR creation much more efficient. And we have two options that you can use within the software to batch create these DPR files. One option is associating your DPR file ahead of time with your plate barcodes using a simple text file. In this scenario, you would still be importing in your sample information after your runs. The other option is adding the barcode and your sample assignment file all together, and this will create DPR files that contain all of the relevant information, the barcode, the samples, and this uses a CSV file. Just a quick demo of what this looks like when you are creating these DPR files in batches. When you click on the create or generate batch runs button in the software, you will see a window that pops up that looks like this. At the top of the window, there is a drop-down where you can select the template that you want to work off of to thereby generate your batches of DPR runs. We'll start by just using that text file to assign your barcodes to the DPR files. To do this, you click on the Add Plate Barcode file here. Prior to generating these batch runs, you will have created a TXT file that has a list of all of the barcodes for the plates that you are going to be running. The AutoRun system does include a handheld barcode scanner that you can use to easily scan in all of the plate barcodes that you will be running. So you will just select that TXT file using this window that appears here and click Open. The other option is selecting the Add Barcodes and Sample Assignment Files selection here. In this scenario, you will have already created CSV files for each plate that you are going to run. You will name the CSV file with the barcode of your plate. And within that CSV file, you will list out the sample name corresponding to each well. Once you have selected the TXT or CSV files, you will see that window be populated with all of the plate information that you have pre-filled into those files. And then you have a couple options that you can select and toggle on if they are of interest prior to generating your runs. You can add a name prefix to the beginning of the generated run name. So by default, it will provide the name of the template that you have used and also the barcode of the plate. But if you wanted to add some prefix identifier to the beginning of that run name, you can by toggling this button on. You also have the option to automatically export all of those DPR files to a folder location. When you are using the AutoRun system, we do have predefined folder locations where you will put either your DPT or your DPR files. So in this scenario, you can pre-select the appropriate folder and then just click Generate Runs. And these will automatically be exported to that folder. Let's move on to how you would actually start and run an AutoRun experiment. The AutoRun system is run using our momentum scheduling software that you can see here. And this is the dashboard view of the software. First and foremost, you bring all of your systems online. This connects them all to the momentum software. And then to start a new experiment or a work unit, you will click on this button that has a big green plus sign. Doing this will bring up a work unit window here. And this allows you to select the type of workflow that you want to run. So again, you have the option to run a dPR run or a dPT run. You also want to designate the number of plates that you are running as part of this work unit. And this goes into the iterations box. You will click Add. You will get a verification window just to designate where your plates should be placed in the system. And then you will close out of this window. At this point, you will see that you have the option to select the Run button, which is the play button here. And doing so will move your work unit to the progress status box. If you have selected a dPT run or a dPT workflow, you will then be prompted to select which dPT file you would like to apply to all of the plates that are part of that run. You will see this momentum message pop up, and you will use these 3 dots to navigate to that folder and select that specific dPT file that you created for this run. I mentioned how the system is a very convenient system earlier, especially for multi-user workflows. So I'll talk a little bit about our capabilities around that now. So you could have several people all put their plates in at the same time, and they'll all run till the end. But you also have the option to continue to add more plates to a work unit over time. I'll describe a work unit versus a batch so that you can better understand some of the terminology here. So when you're running a run in momentum, this larger run is considered a work unit. A work unit consists of 1 or more batches of plates. I could have started a batch of plates several hours ago, and if you personally wanted to come in and bring your plates, you can now add another batch. This is an option that is only available in our hotel configurations. Our hotel configurations can have up to 60 plates on the system at once. So if I had already loaded 60 plates onto the system, you would wait for some of the plates to have been completed. Those can be unloaded, and then you can add more plates to the batch, again, up to 60 plates. To add an additional batch, you will select this icon in the Work Explorer here that is a calendar icon, and it will bring up a window that gives you some options that you will need to select. The first is you'll select that type of workflow that you're running. Again, you have the option of a dPT run or a dPR run. If you want to name that batch something specific, such as Chandler's run, you can. You can put it here or just leave it at the default. You will indicate the number of plates that you are adding within this batch. And then you can also designate the priority of your batch. So if I was running a batch and you are bringing your batch over and your batch is more important than my batch, you can actually give your batch a higher priority. 0 is the highest priority, 10 is the lowest priority. So you can give it a lower priority number. And this means the next time that the robot goes to grab a plate, it is now going to start running your plates ahead of mine. Once all of the batches within the work unit are complete, you will see that work unit moves to the waiting for unload status box. At this point, you will see an unload button appear. You can click on this and you will get a window asking you to verify that you have removed all of the plates listed from the system. So you'll physically remove them and then click verify. There are several files that get generated throughout a work unit. Some of them will get exported automatically to a folder termed the data output folder. And then we also have a momentum run status reports folder where you will get some exports of run status reports. And I'll talk a little bit about each of those types of files next. There are 3 different types of files that will get generated after every single Absolute Q run. And these are going to get automatically exported to the data output folder. The first is a ZST file that we talked about earlier. This is your completed run file that has all of the data collected throughout the run. You will also have various log files that automatically get exported, and these are great to use for troubleshooting purposes. Lastly, you will get CSV files generated with various analysis information. You will get a summary file of your analysis, but if you're also interested in raw fluorescence data and data across the various channels, these will also be accessible in these various CSVs that are generated. At the end of every batch, there will be a CSV file that gets created that is a run status report. This report will have information about each plate that was part of the batch. This includes the barcode, the run status, so this will tell you if it completed as expected or if there were any issues along the way, the location of that plate in the system, and the time in which it was placed there. And these, again, are exported to the Momentum Run Status Reports folder. Once you have several ZSTs that you would like to analyze together, you can combine them into a study, as I mentioned earlier. A study is a group of completed runs, or those ZST runs, that you are analyzing all together as one. This is the same experience that you would have analyzing a single run. You can create a study of up to 24 runs. So this is up to 384 samples into a single study. These studies must be run on instruments that have compatible settings, and you also need to have compatible settings at the file level. So any groups that have the same name and group settings, including the dyes, the target names, the analysis type, and the thresholds, can be automatically merged into a single group. And I will note that those original ZST files will remain independent from the version that is copied into the study. If you do make changes to that run or that ZST file, this will not impact the information that is in the study that contains that run, and vice versa. I hope that was a helpful way to learn about how efficiency can help you in your digital PCR workflows. Thank you for joining us today, and I'll take any questions now.
Thank you so much. That was a fantastic presentation. We have time for just a couple of questions, so I'll read those that have come in. The first one that we have is, which format of plate holders is best to use for labs with multiple users running multiple different experiment types?
Yeah, it's a great question. So we have two different plate storage options. We have the stacks and the hotels. The stacks is great if you are prepping many, many plates all at once. Usually it's by one user, and then you are walking away and you are making no changes to your work unit. The hotel option has a lot more flexibility. As I showed you earlier, you can continue to add batches as the system is running. There's just a lot more flexibility if you do have multiple users.
Great. And this next question is, it's almost in the same line. I run different assays in sequence. Can I set up multiple experiment types in a single batch run?
Yes. So in that case, this is a perfect example of why you would use a dPCR run, where you are assigning each plate a specific protocol, and they can have analysis settings predefined as well.
Great, and that actually answers part of the next question is, can I preset analysis settings ahead of time while using the auto run? And does this include sample names and thresholds for individual wells?
Yes. So when you are completing or preparing those DPT files, your template files, then you can reference those as you are batch generating your DPR files, and everything that is contained within that template file, including those analysis settings, is going to get transitioned into each DPR file.
Fantastic. Thank you so much. I wanted to thank you again for your presentation. It was fantastic. And thank you to all of our participants for engaging with us with these questions. If we did not get to your question, we will, of course, follow up by email after the event. But thank you again, and thank you for your participation.
Thank you so much, Christina. And thanks, everybody, for joining.
Now we're going to be moving on to our final speaker, Dr. Dave Bauer, who's going to be covering the foundations of digital PCR. Dr. Bauer received his PhD in molecular biophysics, investigating genome packaging and DNA viruses. He then spent several years working in DNA forensics and methods development for bioanalytical assays. In 2020, he joined Thermo Fisher Scientific as a field application scientist to support real-time and digital PCR, before transitioning into his current role of digital PCR product application specialist. Just as before, we encourage you to participate by submitting any questions you may have during the presentation. Simply type these questions into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. Dr. Bauer, you may begin your presentation.
Thanks, Christina. So today I'll talk about the foundations of digital PCR, unlocking the power of consistency for improved accuracy in analysis and applications. In this talk, we'll overview some fundamental principles of digital PCR, as well as go through some of the statistics related to it and how that plays into the consistency considerations for our data. We'll also talk about specifically the QuantStudio Absolute Q digital PCR system and the microfluidic array plate technology. And we'll end with a couple examples of digital PCR applications. So what is digital PCR? It's a method to evaluate nucleic acid targets. And you might have thought already when you heard that about gel-based PCR, where in this case we do PCR, and then afterward, as an endpoint detection, we can get a qualitative assessment of our results, where here we can see the bands indicating our target was there or not. And this is a qualitative approach. If instead we want something that is quantitative, you then might think of real-time PCR, where in this case we get those amplification curves that allows us to get quantitative but relative information. So if you were doing absolute quantification, if you wanted to know, for example, the concentration of a target, you would only be getting your CT values, which are relative measures, and then you'd need a standard curve. You need some kind of reference material to build that standard curve to get absolute concentrations for your unknown samples. But for digital PCR, we can get that absolute quantification without any need for reference standards. We're directly measuring the concentration of target in our sample. Before we get much further, I just want to go over highlight some of the benefits of digital PCR. And a lot of those benefits, they come from some foundations of digital PCR related to separating that reaction mix into many, many micro reactions. So indicated here in this picture, we're going to take our liquid, our PCR reaction, spread it across all these individual micro reactions before digital PCR, before thermal cycling occurs. And one big benefit of that micro reaction process is it lets us leverage Poisson statistics to get that absolute direct quantification without any need for reference standards. And those two things combined also give us an ability to have high precision in our result, which lets us confidently measure small changes in our target abundance. And that can be important if you're doing absolute quantification, if you want to know the viral copies of a genome per microliter at an absolute level, or even if you're doing relative quantification like gene expression, having that high precision can be of value. Another benefit of the separating the reaction into microreactions is the sensitivity to analyze rare targets when they're in a background of very abundant wild type or related sequences. So in this case, that red highlighted molecule in the bottom right, indicating that that's the rare target we're interested in seeing. And normally doing real-time PCR or bulk PCR, there'd be competition between those related sequences, which would make it difficult to detect the rare target. But with digital PCR, by having reactions in these individual separate microreactions, it lets that rare target act on its own or with less competition. Additionally, because our target molecules are inside of the microreactions, we can measure linked or intact molecule events. So we can assess to see, is my molecule physically intact, whether that's a plasmid, a viral genome, or an RNA molecule. We can test to see if there's physically linked targets on the same strand of nucleic acid. Now, a second important aspect on the left for digital PCR is we're generally utilizing endpoint detection. So this little picture is showing for real-time PCR, where we have that amplification curve, and from it we get a CT value. The CT value being where that red amplification curve crosses that horizontal line. In that case, the CT value, the output of real-time PCR, it's dependent on the efficiency, the PCR efficiency of our reaction. And there can be times where maybe the efficiency of that PCR reaction isn't 100%. And that means with the same starting quantity of nucleic acid target, you can get a shift in the CT value because of changes in the efficiency. So for real-time PCR, that can be a big problem. But for digital PCR, we're doing endpoint detection. So you can notice those two red curves, even though their efficiencies might be different, the ending value, as long as we end up with high fluorescence signal by the end of our PCR cycling, that's all that digital PCR cares about. And the reason that's so important, for one reason, if you're looking at samples where there's maybe some inhibitors present, so this gives digital PCR an more robustness, improved tolerance to those PCR inhibitors that might be common in samples for environmental testing or wastewater, anytime you have dirty inhibited samples. Another benefit here is that we can do enhanceability for quantifying low abundance targets. So whether that's a low concentration viral target gene, or if it's gene expression where there's very low abundance of that particular gene expressed, the ability to look at the endpoint detection, again, just makes us not dependent on that efficiency, which often you can get a lot of variability when you're dealing with high CT values for real-time PCR, but we don't see that variability at the endpoint detection necessarily. And lastly, the endpoint detection also makes it easier to multiplex targets together. If you've done in real-time PCR trying to do a high multiplex quantitative assay, you might have seen that the assays can compete for resources, changing the efficiency of one assay, changing the CT value, making quantification difficult. But with digital PCR, again, that endpoint value makes things a lot more robust to any variations in inhibition. So I know that's a lot of information for one slide, but I really wanted to just early on mention these key aspects on the left of just what makes digital PCR unique, the microreaction aspect, the endpoint detection, and then how it lays a foundation for all these key benefits listed on the right. Maybe at this point, you may have identified some important aspects on the right that link to what you're doing in the lab, and maybe now you're thinking about how digital PCR might help your experiments. And we'll dive into a lot of these topics a bit more going forward. So let's talk about how we deal with data for real-time PCR, and that'll just set the stage before we look at data generation in digital PCR. So as a reminder, for real-time PCR, we have our reaction mix here at the top, and we're going to look at the thermal cycling, look at the signal of fluorescence as a function of PCR cycles. That's where the name real-time is coming from. We're checking the signal as the reaction is going. And the idea is that any target molecules that we have in the very beginning, they're getting amplified with each PCR cycle. Each amplification event generates some fluorescent signal. And then by the end, we have an amplification curve that we can look at. So by measuring fluorescence throughout the real-time PCR reaction, we see amplification curves, and again, we then take a threshold, that horizontal line, to get a CT value. That CT value, remember, it's a relative measure. It doesn't give you a direct concentration in itself. It's a relative number that needs other CT values for interpretation. But you can see the reaction dynamics, and that's important because the CT is dependent on how the PCR efficiency was. But let's say that I don't necessarily care about a CT value, and even though I'm doing real-time PCR with my amplification curves, maybe I only just want to know, was my target there or not? Was it present or absent? And in that case, you don't need the entire amplification curve to make that determination. Looking at the endpoint signal, where when the target's present, the signal's high. When the target's absent, the signal's lower. That endpoint detection gives you the ability to make that distinction. And that's going to be important when we talk about digital PCR. All right, so let's change gears, focusing on data generation in digital PCR. Again, we have that PCR reaction mix, going to be very similar starting material that we have, but in this time, instead of thermal cycling right off the bat, we're going to create those micro reactions. We're going to separate that liquid into thousands and thousands of individual micro reactions. And I've just got a handful shown here in this cartoon. But the idea is that these microreactions are so small on the nanoliter scale or less, they're so small that many of them don't actually have any target present, while some do. And that's an important aspect of digital PCR, where some of the chambers are empty, some have our target. Then, after the microreactions are set up, we then do PCR cycling, and now we do our endpoint measurement. And in this case, you can see any of the microreactions that had target, they're going to have higher fluorescence signal indicated by the green boxes. So now we can see which microreactions had our target and which didn't. And generally with digital PCR, we want to look at this data for many thousands of microreactions. So to do that easily, we make these scatter plots shown here, where on the horizontal axis, that's all of our thousands and thousands of microreactions going from left to right. And then the vertical scale is the fluorescence intensity for each microreaction. And the expectation here is that you'll have a cloud of high signal representing the chambers that had target in them. And then you have a cluster at the bottom of low signal representing the microchambers that did not have target present. But we also use a threshold in digital PCR represented by that horizontal line there to just make a clear cutoff distinction to say anything above that threshold line, I'm calling positive, and anything below it, I'm calling negative for my target. So that means the green dots that are a little bit lower than the other ones, that doesn't play into the analysis. If the green dot is above the line, it's just counted as positive. And that's actually where the idea or name of digital PCR comes from. We're converting this analog continuous measure of fluorescence into a bunch of digital 1-0 yes-no binary outputs. So at that point, with those simplified binary outputs, yes, no, positive, negative, we can just count them up, count up our microchambers for positives versus negatives, and those values give us a concentration. So just by counting up how many, in this case, 3,600 positives out of 20,400 total, we see that the concentration is around 450 copies per microliter. And that's the concentration of that initial PCR reaction we started with in the upper left corner. But if I told you that I had 3,600 positives and that if you knew that this reaction mix was 9 microliters about, you might do some quick mental math and say, that should be around 400 copies per microliter. Why is it 450 as indicated in the center there? And the reason for that is that not every positive above threshold chamber is going to represent exactly one and only molecule of our target. You can have microreactions with multiple, and it's actually very expected that you're going to have your target, multiple copies of them landing in the same microchamber. And so we need to account for that. And that's why the 450 copies per microliter isn't matching 400. And the way we account for that difference is with Poisson statistics. And just calling out the important distinction of counting molecules versus counting microreactions. Digital PCR actually counts microreactions, although you might hear people in just a quick elevator pitch kind of style mention counting molecules, but I find that sometimes causes confusion when you're doing digital PCR and trying to make sense of your data. So remember, we're really counting microreactions, then we're leveraging Poisson statistics to get a concentration of our molecules. So let's do a quick dive, a little bit of a tangent on Poisson statistics, just to show that it's not a magical transformation that happens. It's rooted in math and statistics. So Poisson distribution, this example, very simple. Let's just say I randomly dispersed this cup of red balls into this grid of squares. And let's say I knew ahead of time that I had exactly the same number of red balls as I did number of squares in the grid. So you could say the effective quote unquote concentration was 1 ball per square on average. But knowing that it was an average concentration of 1 ball per square, I think you would intuitively know that you wouldn't expect to see one and only one ball landing in each and every square individually. Instead, there's going to be some variation. Some of those squares will have no balls in them. Some will have 1, 2, or 3, etc. And if we're dealing with Poisson statistics, notice that lambda character that just popped up. That symbol is meant to illustrate that average concentration, in this case of 1 ball per square. That's what lambda would be representing. So knowing that lambda value in Poisson statistics, without even having to dump the balls into the grid, Poisson statistics can tell us what is the expected proportion of squares having 0, 1, 2, 3, etc. balls in them. And that's just by knowing that average value. Also note that the distribution shown on the right, those distributions change based on the lambda value. So if you have 2 balls per square on average versus 3 or 5, you're going to get a different amount of chambers having, or squares having 0, 1, 2, etc. balls in them. But what I want you to really focus on in the distribution is the leftmost bar, the empty, where there's 0 balls in that square. That proportion of empty, that's going to be directly related to the lambda value. As lambda goes up, as we have more balls per square, the amount of empty balls goes down. Now let's rethink this experiment real quickly. Let's make it closer to digital PCR. In this case, we dump the balls in the grid, but I can't see the balls anymore. All I see is that some of the squares that have any number of balls, 1, 2, or 3, they're just lighting up really brightly red. That's all I know, is that there's some number of balls present in them. In this case, we don't know the initial starting amount of balls. All we see is the count of lit up squares. So we can use that information though, because even though I can't see if there's 1, 2, or 3, I can see that how many of these squares are empty versus not empty. And so I'm kind of blind to most of the Poisson distribution, but I can accurately assess that first column, the empty proportion. And that's what we're going to use with digital PCRs. We're going to measure the proportion of empty reactions, or in this case squares, to then estimate our lambda value. So let's say we've done that here. After the balls were dumped in, counted up how many of the squares were empty, and it looks like it was 37% of the squares are empty. I don't know anything about how many had 1, 2, or 3, but 37% were empty. Using Poisson statistics, I can plug that measured 37% into this equation to now get that lambda value back, and I can see, oh, I must have started with 1 ball per square on average. And stepping a little bit closer to digital PCR, instead of 1 ball per square, we'd think of that as 1 copy of my nucleic acid target per microreaction. But if your instrument told you had 1 copy per microreaction, that's a difficult number to have an intuition for. So we then convert that by simply knowing what's the volume of that microreaction. And now lambda can be expressed instead as a concentration in real units. Copies of our target per microliter in this case. So that's all the math we're going to go into for Poisson statistics. The key takeaway there is that there is a direct relation between the proportion of empty microchambers, something that you can physically observe in the experiment, and that directly relates to the concentration of target that you started with. So that equation we saw before, we can actually just map that out all the way across the dynamic range here, looking at the copies of our target along the horizontal and the proportion of negative reactions on the vertical axis. And so this is just showing if we measured 37% for negative, we can use this equation that's shown by the line to then convert that to our concentration, 2,300 copies per microliter. And remember, we're doing this based on a theoretical statistical principle. There's no references involved. We're not comparing to any calibrator samples or anything like that. It's just a direct measurement coming from the sample itself. But digital PCR and Poisson statistics can actually take it a step further. Not only can it report out that concentration value, here 2,300 copies per microliter, but from a single measurement, we can also get a measure of uncertainty associated with that value. And that's represented by the shading along the concentration axis. The idea here is that we can report out how confident we are in that 2,300 copies per microliter. How precise is the measurement? And that's often shown in a 95% confidence interval coming from the Poisson statistics. And that's important because if you measured 2,300 copies per microliter, you want to know if is it meaningfully different from another number. Let's say another measurement gave me 3,000 copies per microliter. Seeing that confidence interval there, that tells me that I can have confidence that it's a significantly different value than 3,000, for example. Another way that in digital PCR, we can talk about this as the precision, where in this case, I can get the idea that this is a fairly precise measure, 1.8% from that 2,300 that I measured. But I want to call out, though, that the concentration, and especially the precision or confidence interval, that size of that area, depends on exactly what concentration we're landing in. So if we're very far from the middle, so in this case, getting at smaller concentrations, we're going to get a less precise measurement. And this is specifically just from the statistics of Poisson. And we can actually look at this to see that there's, in fact, an ideal concentration, that lambda of 1.59, where we get the best precision. And for our absolute Q system, that's going to generally be around 3,700 copies per microliter. That's where you'll have the best precision. But every time I show this slide, people then get worried to think, so I have to know the concentration before I measure it to get good precision? Is that what you're saying? And no, that's not at all what I want to say. Even though the precision is variable across the concentration range, it's still very precise regardless. So here's an example showing if I'm at the really low concentration end, 10 copies per microliter, this would be a fairly high CT, up in the 30s if I did real-time PCR. And what I'm doing is comparing it to a known twofold difference. So you can see that the 10 copies per microliter versus 20, that's where the average value, the measurement, is landing. But notice the size of the error bars. That's a pretty less precise measurement, meaning I can't confidently say that this is exactly a twofold difference. I could confidently say it's around 1.4 to 2.9, somewhere in that range. But if I repeated the same measurement with higher concentration, here 100 and 200 copies per microliter, notice that range of what that fold difference would look like. It's getting smaller, closer and closer to 2. And that'll keep happening as I get closer and closer to that ideal precision area. So you can get very precise measurements, and as you start to get higher and higher concentrations, the error bars will start to get wider again, giving you less precision in that fold change estimate. But the important idea is if you don't need the precision to say that it's exactly 2-fold versus 2.1-fold, then you have a pretty wide range of concentrations that you can confidently operate in for your experiments. So we do have a high degree of precision in digital PCR, and that precision is influenced by concentration, as shown here in these graphs. But there's another thing that impacts the precision of your measurement, and that is the number of microreactions actually used. So in this example here, we're assuming the same number of microreactions every time. But let's say we had a system where the number of microreactions was variable. So now let's say I'm looking at a 10% change in concentration. That 10% is meaningful for my workflow. And I can see with my 20,000 microreactions, the error bars are not overlapping. I can have some confidence in that 10% being a real value. But as the number of microreactions decreases, if it's something that varies run to run, experiment to experiment for the system, then you might see that the error bars with lower numbers of microreactions that day, the error bars start to overlap, and now I don't have the ability to confidently say that that's a real 10% change. So the number of microreactions can add another level of variability in your results. And that's generally an extra variable is not something you want to deal with in science. We want the least number of variables possible. So that's where having consistency in your number of microreactions, consistency in your dPCR workflow can be a very important aspect. So we just hit over points 1 and 2. And I'm now going to transition to talk about the Absolute Q and specifically the microfluidic plate technology used with it. And I left you off on that cliffhanger of how important consistency can be in digital PCR. So let's actually look at some consistency comparisons for the microfluidic array plate technology. Here we have 128 different comparisons across different plates, different runs. And what we're looking at is the number of microchambers that were actually accepted and used in the digital PCR analysis. The maximum possible is 20,480. That's how many microchambers the plate has per array. And you'll notice that the vast majority of these 128 comparisons are very close to that maximum 20,480 indicated by the arrow there. There's a handful that drop a little bit lower, but notice they're not dropping far. The Y scale here is going from 21,000 to 16,000. So those drops, they are fairly small, and we're still up around 20,000 or more consistently. And you can see that the average across this set is 20,413, meaning on average, we're only losing a couple of dozen of those thousands of microchambers. Very consistent result. And we also have consistency, not just in the number of microchambers that are utilized, but also in the actual dPCR data itself. So this is just showing a sampling of the different Abby and June targets in the assay, seeing that consistency plate to plate, run to run. But in the end, with digital PCR, it's the concentration is one of the important metrics that you want to read out. And this is now just looking at 105 replicates, looking at that concentration comparison where you can see we are getting very consistent, very reproducible values. And this was run not as a single plex, but actually as a 4-target assay. So a bit more complicated PCR chemistry involved. And even under those conditions, we are seeing nice, consistent results across plates, across runs. So a lot of the consistency aspects, it plays into the consumables, the hardware that we're dealing with for our digital PCR system. And this is just a high-level overview to mention that in the digital PCR process, we prepare our chemistry, very similar to what we would do with qPCR. Then comes in the critical step of isolating that prepared reaction mix into the many thousands of microreactions, followed by the PCR thermocycling for amplification, and then some image capturing and quantification at the end. It's that step of exactly how we create our thousands and thousands of microreactions that's a really important part of the digital PCR process, and it plays a really valuable role in the consistency and quality control that you have available in your data review. So let's talk about how that happens, that kind of hands-on aspect of creating a digital PCR run with the QuantStudio Absolute Q workflow. So this image in the center is showing that MAP16 plate. That MAP16 plate has several of these loading ports circled. And in that loading port, that's where we're going to use a standard pipette, introduce 9 microliters of that PCR reaction mix into the port. Straightforward step. And then we'll follow that with an addition of 15 microliters of the isolation buffer. And with those 2 strokes of the pipette, you've effectively set up your digital PCR reaction chemistry. The only thing left to do is just to apply quickly by hand these gaskets over those loading ports, load the plate into the instrument, and then at this point, the user can walk away. Because that plate inside the instrument, it does all of the sub-steps of digital PCR. It sends that liquid in across all the different microreactions. It does the PCR thermal cycling and the image acquisition. All of that happens inside of one instrument, meaning there's no touch points from the user. They load the plate, walk away for around 90 minutes, come back to the digital PCR results. Looking a little bit more detail of that MAP16 plate, there are 16 samples that we can run at a time, shown there in the image with those 4 columns of 4 rows. But what's also valuable is you can run partial plates column by column. So let's say I just need to do a quick pilot test just to see how things are looking in my sample, or I just don't have a lot of samples to run today. I don't need to wait and batch till I have 16 samples so I don't waste any part of my plate. Instead, I could just run 1 column of 4 and then get some results. And then immediately after or days later, I can then run remaining columns that are unused separately. So this adds a lot of flexibility, convenience to the workflow for the user. And if we zoom in, looking at those individual arrays, how they're connected to the microchambers, this is an important part of the consistency for the MAP16 plates. These microchambers, they're physically defined inside of the plate itself. And so the liquid just flows through where it has to go. And that's why we get that consistent definition of 20,000 plus microchambers time over. And it also gives us very little dead volume. So if digital PCR, some systems, when you add some amount of PCR reaction mix, not all of it ends up being part of the actual analyzed information. Some of it gets wasted as dead volume. But with this system, very low dead volume, less than 5%. So we're utilizing a lot of our reagents. We're not throwing away any of our sample, which means we're less likely to miss any low abundant targets that we might have in our sample. And in the end, confidence in our data is what we want. So we know that digital PCR can give us high precision, especially when we have consistent number of microreactions. We can predict confidently what those precisions will look like. That consistency is very important for that, as well as the accuracy in our result. And what's indicated in that last picture, the red is showing that we have a special loading die in the master mix. And that's so that the system can confidently say, does the microreaction, every of the 20,000 plus individual ones, do they actually have the reaction mix present? Did it load properly? And that's really important for data confidence. Speaking of data confidence, something else really valuable for the QuantStudio Absolute Q, the idea of auto false positive rejection. There are some ways that the system, because of its unique design, can really give you extra quality control benefits. One of which is the per run background subtraction ability. That plate doesn't move around throughout the workflow. It stays in its spot where the user left it in all the digital PCR throughout the entire digital PCR workflow. And that means that the instrument is capable of taking background images of each and individual array of each of the different fluorescent channels we're working with in that experiment, save that background image in case there's any fluorescent material that might be interfering, as indicated by that little fiber shown in gold there. Normally, some systems might have trouble saying if that's a real signal or not, but our system subtracts that signal that it observed early on from the final result, meaning that autofluorescence or that artifactual fluorescence isn't likely to have much impact on the final results, won't interfere with our data analysis. So that's the background subtraction that happens. Additionally, there's another level of quality control. Because that plate is stationary, the image is taken of each microchamber, and at a microchamber level, there's another quality control that looks to say, yes, it's bright, But does the distribution of pixel intensities look like real PCR signal, or does it look like some other artifact? So that means the system can automatically flag chambers that might be bright but don't look like real PCR signal and remove those from the analysis, again, reducing false positives. And so the idea is that that stationary plate for the digital PCR workflow really does add a lot of value to let a lot of this extra quality control happen in the data analysis. And this is all automatically done in the system. The user doesn't have to worry about it. And there's actually multiple levels of quality control that I want to call out. I just mentioned the analysis level where there's the background subtraction, that microchamber evaluation that automatically occurs. Additionally, I mentioned that ROX loading die that we use in the master mix. That's important because this helps us know that we have consistent loading of those 20,000 microchambers. So that cloud of red that's shown there, that's the ROX die intensity. And whenever you have microchambers that have a lower or higher value, something that's outliering, not inconsistent, those microchambers get removed from the analysis before they have any impact. And additionally, on the bottom center there's also results QC flags built into the software. So there's several other analyses that happen, and the user will be alerted to say, hey, this result has something unusual about it. You might want to investigate further. And also the user level, the user itself has the ability to review those array images, see how the pattern of positives looked, investigate for different colors, as well as look at the data metrics that are reported. So not just the concentration, but a lot of quality metrics like the 95% confidence interval, the precision measurement, the lambda value, things that let you additionally assess to know what level of confidence I can have if I'm comparing concentrations to each other. So just a high-level recap on the QuantStudio Absolute Q system. Some key benefits: it's a single instrument, meaning it's an easy workflow. Load the plate, walk away. You walk away for 90 minutes, and now you have your digital PCR data completed. That consistency aspect, we talked a couple of reasons of why having consistent numbers of microchambers run to run, plate to plate is very important for precision. And that idea of very little reagent loss. So very little wasted reagent, little dead volume means we're not throwing out our expensive chemistry reagents. We're not throwing out our precious sample. We're not throwing out any rare targets that we're trying to identify. And that flexibility of the plate itself, you can run it column by column, meaning you don't have to wait around to get a full plate. You can conveniently just run anything that you need as you go. And multiplexing. This system is a 4-color capacity for your targets with a 5th color reserved for that special loading die that we talked about. And at the bottom there, the quality control, especially auto false positive, but as well as false negative rejection, giving us that confidence in our data. And this is super important, this auto false positive, when you are dealing with those rare targets. Because if you only are expecting a handful of positive microchambers, you want to know that the 1 or 2 that are showing up positive are real as opposed to some other artifact. And that's where this false positive rejection is very valuable from the MAP16 plate. All right, lastly, we're just going to go through a couple examples of digital PCR applications, especially where consistency is an important factor. So one of the extreme benefits of digital PCR is the precision that it offers. Very good precision in digital PCR. And this can be very important for copy number variations because we have very small differences in the concentration, the abundance of the target from different CNV values. So this is an experiment showing where we're investigating spinal muscular atrophy, looking at alleles that are related to that. And then this is a 4-plex chemistry, meaning we're getting a lot of information from the run by making use of multiplexing in the digital PCR experiment. I don't want to dive into the details of the system itself, but really just calling out the importance of consistency and precision. Here, we're looking at the results from many different samples, measuring the CNV values for these two different versions, SMN1 and SMN2 alleles. And you can see when you have higher numbers, 3, 4, 5 copies per genome, you need really good precision to accurately, confidently identify that 5 versus 4 versus 3, or even as high as 6. So that's shown here. And so by having the high precision, that precision benefits from consistency. Having those aspects from the Absolute Q system makes those measurements much easier to perform. Very similar to that, gene expression. In this case, we might be looking at RNA instead of DNA as the target, but it's really the same idea of we might need precision. If I'm doing gene expression with digital PCR, so two common reasons you might want to do that is if your target is simply low abundance, because if you have very high CT values, you have very low precision with real-time PCR. So we can leverage better precision at those less abundant targets with digital PCR. Or even if it's a pretty abundant target, if you're looking for very small fold changes, if those are meaningful for your system, digital PCR can help. And this example plot here is just showing real data looking at a reference sample versus plus or minus 10% changes in that concentration. And you can see the consistency in those triplicate measurements showing us that we have the confidence to call accurately a 10% change. And just a reminder that if you're thinking about doing gene expression with digital PCR, it's generally recommended that you still would use an endogenous control gene, just like you would with real-time PCR. But since it's easier to multiplex with digital PCR, having that multiplex reaction really helps enable better precision in your gene expression measurements. And instead of delta-delta CT, instead you can have a ratio of ratios of concentration from the digital PCR measurement. But the main takeaway is that even though you're measuring an absolute concentration for gene expression, you still want to normalize into a relative measure. Because if I found out that there's 200 copies per microliter of my gene, that doesn't really say much because you have to account for variations in the RNA extraction, the initial sample quantity, all of those upstream things that get accounted for by having that endogenous control gene utilized. And again, if you're doing digital PCR for gene expression, that consistency really helps enable high precision, and that might be one of the key reasons you're looking into digital PCR for gene expression. Last one I want to talk about, molecular integrity. This is something pretty unique to digital PCR. It's very difficult to even consider an assay that would do this for real-time PCR. Let's say that I had some molecule, whether it's a viral genome, a chromosome, or even an mRNA molecule, and I want to know the 4 different locations represented by the blue, green, yellow, and red data, these 4 different targets across 4 different positions on my molecule. I want to know if they're physically connected on the same strand of DNA or RNA. And so looking at the results here for the concentration values, I can see the concentrations are similar, but that tells me nothing about this quote unquote molecular integrity or linkage in those targets. So there's an additional level of analysis we can consider with digital PCR, and that's actually assessing the individual microchambers that are positive for multiple targets. So imagine that in the results shown above that this was a very fragmented molecule where the different locations that I'm assessing, blue, green, yellow, and red on that molecule, they're all fragmented away from each other and they just randomly disperse into different microchambers. By chance, I'll have some co-localization of blue with red, green with yellow, but you can actually see from the data that you don't have intact molecules versus if you truly had an intact molecule, you wouldn't get that random distribution of molecules. You'd see that, oh, this chamber, it has all 4 colors in it, all 4 targets from the molecule. The next microchamber has none, none again, all 4. That co-localization helps you identify that you have not just the concentration of the target, but also the intactness of the molecule. And you can imagine a situation where you might have something that's in between what's shown on the left and on the right. Maybe you have some intact molecules along with some fragmented molecules. So the calculations, the analysis can get a little bit more in depth. And there's a couple of ways that we can review this molecular integrity data. For one, the software will report out the quantifying, the counting up the co-localization events. So for each of the different combinations of your different targets, it can report out what percent or count of the chambers had that combination of targets present. And that's something that's really important if you want to do a molecular integrity analysis. And you can do that analysis in a kind of more qualitative or quantitative approach. So what's shown here is I was to simply make an output like that one shown on the left and just look at the relative percent of the different categories. So we have empty chambers, ones that have only FAM, only VIC, only ABI, the pairwise, and then finally in black, having all three of the targets present. And what you can see here is if I have a purely fragmented sequence versus mixing it with 25% intact, 50%, 75% intact, or 100% intact roughly, you can see that black bar taking up more and more space in the graph. There's a higher fraction of microchambers that have all three of the targets present, as you would expect for intact molecules. You might be thinking, hey, I see numbers. That looks pretty quantitative. But I'd still say that this is somewhat qualitative because you have to be careful when you're interpreting these numbers. For example, imagine if I took that same fragmented material that's shown on the far left and simply increased the concentration of it and then did the analysis again. That's what's shown on the far right. Notice that the size of the black bar, the triple positive count, definitely went up. But it didn't go up because of anything to do with linkage or molecular integrity. It's simply just random co-localization of the individual targets together. So an analysis like this can be useful at a high level, but it does need some careful considerations about concentration normalization to really get a lot of insight out of it. An alternative approach, more quantitative way to do it, is if we can take that same data output, those molecular counts, or the different co-localizations of targets. And we can use, one example here is this website has a DNA integrity calculation that it offers. So you can upload the counts data for the different combinations of your targets, and it can report out some quantitative values. And these quantitative values, they'll take into account the random chance co-localizations of targets, meaning it's not going to be as concentration dependent of a measurement, which is important for any molecular integrity analysis. All right, so let's come back up to the surface, just that highlight slide from early on about the strengths of digital PCR and a lot of the key benefits on the right that it offers. But I do want to make sure that I don't give the impression that digital PCR is always the answer. We've compared things to real-time PCR multiple times in this talk, and that's for good reason, because digital PCR and real-time PCR, they can complement each other pretty well. A lot of the key benefits, the strengths of digital PCR complements the weaknesses of real-time PCR and vice versa. So if you are only using digital PCR, that might be perfectly fine if your experimental questions align nicely with what's shown here on the bullets to the right. But maybe perhaps you don't need absolute quantification for everything in the lab. Maybe relative quantification is all you need. And maybe your gene expression targets are pretty abundant, so you don't need the low limit of quantification that digital PCR offers. So by having the choice of digital PCR versus real-time, knowing which one fits better can be really valuable in just making your overall experimental outputs better. So remember, real-time PCR has some key advantages. One really solid one is the dynamic range. Real-time PCR, you can load a handful of molecules or a billion molecules in the start and still get a CT value. That's a very useful feature. As well as the high throughput, quickness of runtimes, cost per sample, analyze volume. All of these things are strengths to real-time PCR that can complement a digital PCR workflow, or at least let users in the lab decide which one fits today's experiment better. And so with that, just want to conclude calling out that if you want to learn more about the Absolute Q system and digital PCR in general, you can use this quick www.thermofisher.com/dPCR to get more information.
Dave, thank you very much for that informative talk. We have just a couple of questions coming in through the chat, so I'll go ahead and give you those now. So the first question we have here are qPCR primers different than dPCR primers?
In general, no. If you're doing real-time PCR already, very often that primer set, that assay from real-time PCR can be utilized directly into digital PCR without any redesign needed. It's always good to empirically check, just do some pilot tests to make sure things look good. Maybe there's very minor optimizations in the thermal conditionings that might be needed between the two platforms. But generally, I've seen plenty of examples where users just take their qPCR assay, throw it into the Absolute Q, and things look great.
Fantastic. And this next question actually pairs very nicely with that one. This one says, what are the most important things to consider if I want to test more than one target in the digital PCR reaction?
So that plays to one of the key benefits mentioned early on is that reliance on the endpoint detection. That means we're not dependent on the qPCR efficiency. And very commonly when you're doing qPCR, multiplexing for a quantitative assay, you can get efficiency problems. So if you're doing digital PCR, I generally recommend doing multiplexing. Even if you only have one or two targets you're interested in, sometimes you can create clever, useful controls or internal positive controls that you can leverage for the third and fourth dye channels to get more information per run.
Fantastic. And then I have a kind of multi-part question here. So is digital PCR good for dirty samples like plants or agriculture? And if an inhibitor does affect the CT, what does that look like on a dPCR plot?
Yeah, that's actually really similar to the previous one, where it's the idea of not depending on the efficiency of the PCR reaction. So if you have inhibitors present in the sample, which can be very common for certain sample types like environmental testing, wastewater, in those cases, those inhibitors that get carried into the final isolated nucleic acid can impact PCR. And if you're doing real-time PCR, changes in the CT value means a change in your interpretation of the concentration, which isn't necessarily a good thing. But with digital PCR, we don't really care about the kinetics of the reaction, the efficiency itself. We just need that PCR reaction in that microchamber to get enough signal, enough PCR to happen to get it above the baseline level of fluorescence noise. And at that point, it can be counted as positive. So even if you did have severe inhibition, maybe the overall height of the scatter points, the fluorescence signal might decrease a little bit. But again, that's totally fine because if it's above threshold, it's counted as a positive, and that's all the Poisson statistics cares about.
Fantastic. And our last question is, do I need to be worried about bubbles when pipetting into the digital PCR plates?
In my experience, no. We don't want to intentionally introduce bubbles for no reason, but I've played around with myself just kind of viciously pipetting into the plate and seeing that even if there is a bubble or two created after the loading process occurs where the instrument sends that liquid into the microfluidic plate, that usually dissipates a lot of the bubbles that would have been present and generally don't have any impact on the results.
Fantastic. Well, thank you again so much, Dave, and thank you again for all of our attendees and the great questions.
Yeah, happy to be here.
Thank you again to all of our speakers and all of our attendees for joining us today at the second session of For the Love of dPCR 2024. Remember, this virtual event is not just a one-time experience. It's a year-long journey filled with ongoing content updates and insights from invited guests. We encourage you to continue coming back to our virtual environment where you can access a variety of downloadable content. You can also request more information from sales representatives through any of the Contact a Specialist forms that you see throughout the event. Thank you once again for your participation, and we look forward to seeing you back at our next session for more exciting content and opportunities to connect with the digital PCR community. Keep exploring, keep learning, and keep pushing the boundaries of scientific innovation. Thank you again.